Today we talked about some properties of linear vector space, and the first property we talked about is zero is a unique. Zero is unique.
That was not the first, but yes, that was one of the properties, right?
Yes, sir. But the doubt is that you explained that uh,
From the
u
first,
that
yes,
belongs to V
yes,
is equal to uh, 0 prime,
okay, yes,
and it is also equal to 0.
right.
So I couldn't get how they are equal.
Oh, so I said that one, let's start with the hypothesis that there exist two null vectors or the zero vectors. Fine. First,
Yes, sir.
am I audible and is this screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
Yes,
good.
sir.
So let me just quickly explain. So first I started with the proposal that there exist two null vectors, says O and O prime. And then I showed that if such two vectors exist, then the left hand side of the two, I mean, we started by saying let's just start with the basic definition of null vectors and then put u vector to be 0 prime or the O prime vector for one or O for another. And when you did that, what you found, there were two equations. If you look at the left hand side of those equations, then left hand side of the equations are same because of the commutative property of the vector addition. And if the left hand side are same, then of course the RHS is also same. And the RHS was just null is equal to null prime. If you want to know more, I mean, we will discuss in the chat box after the class. Fine.
All right, sir. Thank you.
Yeah, sure. Anyway, so what we were doing yesterday, we basically continued with our discussion on algebraic structure. We defined linear vector spaces, and then we said that there can be real linear vector spaces or the complex linear vector spaces, depending on what kind of field or the scalars we are talking about. Then we discussed certain examples and few properties of the linear vector space. I discussed briefly about the subspaces, and finally we came to this linear dependence and the linear independence of the vectors lying in the vector space. Towards the end, I gave one of the problems and I asked you to figure out whether the set containing P1, P2 and P3, three polynomials, that was linearly dependent or linearly independent. So all you were supposed to do, although some of you answered actually within the class, but all you are supposed to do is to basically write down the equation of the form which we wrote alpha 1 times P1t plus alpha 2 times P2t plus alpha 3 times P3t and equate it to 0. Now please understand that the right hand side, when I am equating it to 0, it is still a null vector of the polynomial space. So it will also have 0 plus 0t plus 0t square plus 0t cube, so on and so forth. So then you are supposed to equate the coefficients of t, t square and t cube and figure out if alpha 1, alpha 2 and alpha 3 are all identically 0 or one or two of those are not equal to 0. So what did you find?
So they all come out to be
All of
zero
them are zero.
So they
And
are
hence that the
independent.
set
Linearly
was,
independent, sir.
because
then hence
linearly
the
independent.
set turned out to be linearly independent. Thank you.
Linearly independent.
Yeah, very good. So let's just continue with this discussion and let me just, okay, give you another set, let's say S, which is consisting of n vectors. So let's say we have n vectors and let's consider situation one. If one of the vector, so this is one of the vector belonging to this set is such that I can write down this vector as the linear combination of the other vectors of the same set. So alpha 1 times alpha 2. Of course, this right hand side does not include this UK, which is here somewhere. So will the set S be a linearly dependent or a linearly independent set?
Linearly dependent.
Linearly dependent.
And why would you say that?
Because we can write that as the linear combination of the other vectors.
Because we can, if we go back to our original equation, we can write down the same equation as minus of uk plus so on and so forth alpha n un is equal to null vector. So all I did that I basically took this vector uk on the right hand side, and hence you are left with zero vector, or you can think of that I added the inverse vector. So additive inverse of uk on both the sides so that your equation look like this. Now once the equation looks like this is the form of the equation which we were discussing yesterday. If one of the coefficients of any vector is non-zero, then the corresponding set will be, so this will have the coefficient alpha k which is equal to, what is coefficient alpha k of this uk? Minus 1, which is of course not equal to 0, and hence this set will be linearly dependent set. So another definition of the linear dependence, one of the definition is that you write down in the equation form the way we have written it, and then just figure out if alphas, one of the alpha is non-zero, or one of the alpha is, let's more than one of the alpha is non-zero. Another possibility is that if one of the vector of the set can be written as the linear combination of the other vectors, then also such a set will be a linearly dependent set. Okay, another question. What, let's say there exists a vector uj which belongs to this set such that this uj is null vector. So there exists in this set one vector which is actually a null or a zero vector. What about the linear dependence or the linear independence of the set?
Linearly independent.
Dependence. If any is
Dependence of
So
Okay, so let's just try it out. Let's just try it out. Yeah, let's just try it. Alpha u1 plus alpha 2 u2 plus so on and so forth, alpha j uj plus so on and so forth, alpha n un. This is the equation which we try to figure out. If all alphas are identically zeros, then of course it is a linearly independent. Now let's look at this, concentrate on this. This vector is given to be a null vector. Now if I multiply any number, any real or a complex number with this, what happens to this? This is still equal to
zero.
Null vector.
null vector. So that means you can always add null vector to any set of vectors with any coefficient, not necessarily zero, and it is not going to affect anything, right? So alpha does not necessarily equal to 0. Still this equation will hold true. Whatever be the other coefficients, if you just think about the coefficient of this vector, then this vector coefficient does not need to be 0 in order for this equation to be satisfied. Which means what? That one of the alpha is not necessarily equal to 0. And hence the set will be, if one of the alpha is not 0, linearly dependent set. So please remember that anytime you are given a set and if the null vector is there, then surely that vector, that set is a linearly dependent set. So while continuing with linear independence and dependence, I'm pretty sure that you would be able to do problems there. But please understand these two important ones, that the definition of the linear dependence is expanded. Any vector, if it can be written as the linear combination of the other vectors of the set, then that set is linearly dependent. And if zero vector exists in that set, then also that vector is, that set is the linearly dependent. Yes.
So would you please explain it again? Containing
Yeah,
null
I mean,
vector that
you understand that with zero vector, this is the last one, right? The last one, the second part or the first one?
last one.
Last one. So if you look at it again carefully, if one of the vector is zero vector in this set, original set, then it doesn't matter what is the coefficient of alpha, and you are still going to get this zero vector, right? Because if you multiply 0 with 0 vector, then also you get 0. The equation will be satisfied irrespective of the value of alpha. Irrespective of the value of alpha. and hence alpha does not necessarily be equal to 0 and then only that the equation is satisfied. Remember the definition for the linearly independence. They must identically be 0, all the coefficients. If any other possibility exists, then the set is linearly dependent. In this case, the possibility exists that you can put any value to alpha, in fact, infinite values to alpha, and you are still getting this equation verified. And hence alpha, since one of the alpha is not equal to 0 whenever one of the vector is a 0 vector. So of course, it is a linearly dependent set. So whenever you say 0 vector, figure out that this is not going to be a linearly independent set. So let me just give you some more problem just to see how it goes. Let us consider two sets. Sir. So one set is U1 and U2, and another set is U1, U2, U3. These are abstract vectors. I am not telling you what these vectors are, but it is clear to you that one set is contained in another set. In fact, in this case, equal to doesn't happen unless until U3 vector is something which is identically equal to U1 or U2, right? So S1 is contained in S2. This set S1 is contained in set S2. So let me ask 4 questions and then we will go one by one to understand that we understand the concept of linear dependence and independence. So if S1 is linearly dependent, can you say anything about S2? If S1 is linearly independent, then can we say anything about S2? Or otherwise, if S2 is linearly dependent, can we say anything about S1? Or if S2 is linearly independent, can we claim anything about S1? So these are the 4 things. So if S1 is linearly dependent, so that means a set of 2 vectors is linearly dependent. What can you conclude about set S2? Is it a linearly dependent set? Is it a
Linearly dependent.
Or can't say?
Linearly dependent.
Linearly dependent because 2 vectors, if they are linearly dependent, then any vectors which, if you add it, I mean, since these 2 vectors are always there, so it will always be linearly dependent. Absolutely right. What about if S1 is linearly independent, so these 2 vectors are linearly independent, what will you say about this S2? Is it going to be?
I can't say anything.
Can't say
We
anything.
can't say anything.
We can't say anything because we do not know about U3, what kind of vector U3 is. It may be independent or it may not be. And hence, we cannot definitely say anything about this. What about if S2 is linearly dependent? So I know that this bigger set is linearly dependent. What can I say about this S1?
Linearly dependent.
We still can't say that.
Can't say.
Can't say.
Depends on the elements of S1.
If it is a
Okay.
proper set, then we
So
can say.
here, the first time I am seeing that there are some, okay, non-uniformities among the answers. Okay, what about this one? If S2 is linearly independent, U1, U2, U3 are all linearly independent. What about this smaller set, U1, U2?
It is linearly
Linearly
So here you all agree. Okay, good. So coming back, if these 3 vectors set containing linearly dependent, do you know which of the vector depends on which other?
No, sir.
You do not know about. Which means you do not know whether U1 and U2 are linearly dependent or not. Right? So what do you say?
Sir.
Here, can't say.
Can't say.
Yeah.
Yes, sir.
So some of the properties of the linear dependence and independence, I mean, if you understand this, then when we are talking about the subspaces and the bigger linear vector spaces, some of the properties of the bigger one. So if S1 is linearly dependent, S2 is linearly dependent. So smaller one if linearly dependent, the bigger one is surely linearly dependent. Or if the bigger one is linearly independent and the smaller one is going to be linearly independent, some of these are utilized in order to move further rather than reinventing it one after another. Okay, so this is something which you have been doing and I understand that you also know it, but I still wanted to do few things regarding that. Questions here so that I can go to the next one. These are some quick, basically concepts which you already know, but I just want to highlight. Now, I would say the word dimension. Okay, there is no need to write dimensions. So dimension of a linear vector space. I would request all of you to mute, and then if I ask the question, then you please. So dimension of a linear vector space. So we call n to be the dimension of linear vector space if the linear vector space consists of maximum of n linearly independent vectors. Okay, let's just say if a linear vector space can accommodate a maximum of n linear independent vectors, then we call that n to be the dimension of that linear vector space. You already know about it because whenever you are saying the three-dimensional Euclidean space or the three-dimensional real vector space, you are using the word three here. What does that three tell you? That there exists maximum of three linearly independent vectors. And here lies our association with the directions of this linearly independence. That remember that in the three-dimensional real vector spaces, you always talk about that there exist three directions, and any vector can be written in terms of those three directions. Now, those three directions basically correspond to those three linearly independent vectors. And hence, several times we associate our linear independence or the set of linear independent vectors with the direction. Although it may not be, I mean, I would say you may not be able to visualize it. For example, if there is an n tuple, so let's just think about it. So if there exists n tuple, remember this is we did yesterday. N tuple is n numbers over a real space. And I ask you, what is the dimension of this space? So what will you say? Remember our n tuple of numbers were x1, x2, xn, and each of these xi belonging to this real space. So what will be the dimension of this space? How many linearly independent vectors this n tuple will be able to accommodate? So if it is three dimensional, let me just go back. X1, X2, X3. If it's a three-dimensional space, this is what we call three-dimensional. So what is the basis of calling it three-dimensional? That it can accommodate maximum of
three vectors.
Three directions.
three linearly independent vectors or three directions, right? So if you have n tuple, collection of n real numbers, what will be the dimension?
N.
Obviously n. In fact, if you can think of, there is already an answer written here. I wrote this small n as the superscript. So it's a common way to write VNF as the n-dimensional vector space over a field. So this is n-dimensional real space over real number. Okay, let me just see if we can understand it. So if I ask dimension of collection of polynomials with degree less than or equal to n.
N plus 1.
And why would you say n plus 1?
We have the one.
Because we have a constant.
Because of the power of t power 0.
So this is how we wrote it. Yeah. And collection of number A0, A1, A2, if you continue to do that, since there is A0 also, so you said n plus 1. So there are n plus 1 if these coefficients are defined basically. So it cannot accommodate more than n plus 1 linearly independent vectors. Okay, let me just see if you can say something about dimension of 2 by 2 matrices over real space.
Two dimensions.
Two dimensions.
So let me tell you what will be the most generic matrix. Let me ask you. Most general 2 by 2 matrix. A, B, C, D. Where each of these A, B, C, D, they are the real numbers. Each one is real number. So now can you think about it? How many independent numbers do you want to have in order to have this generic matrix?
4.
4.
That is 1, 2, 3, and 4. That means 2 into 2 is equal to 4. In fact, you can generalize this concept and say dimension of M n cross P over a real space. This will be how many?
N cross P.
N into P.
NP.
N cross P or NP, right?
N into P.
No, not P into P, it is N cross P. So depending on how many of those numbers are there. So please see that dimension basically just tells you that this linear vector space holds the maximum of these n linearly independent vectors. Now this is interesting. Why? Because think about a vector space. Whenever you think about a vector space, how many vectors actually live in the vector space? Can anybody guess? How many vectors live in the vector space?
Finite.
Infinite. And
Infinite
why would you
vectors.
say that? Why would you say that? It's the right answer.
Because numbers doesn't end.
We can have
So
any number
as
of
far as you can.
independent
The
vectors.
vector space is defined over a field, which field can be real number or complex number, 1, right? And every vector of the form this also belongs to the vector space, right? So how many real number or complex number you can think of? Infinite many. So that means even if there exists one vector, let's say null vector, then also if you just keep on multiplying with all those numbers, then these will be infinitely many numbers. And this is a trivial example, but in any other case where you have more than one vector, you will easily think of that any multiplication of this number with that vector will still produce the vector in the same space, and hence there will be infinite many. Now, out of those infinite many vectors, you can always think about certain number of vectors which are linearly independent. And why that concept is important? Because we are going to one very important concept which we call as the basis. Can anybody tell me what is basis? This is what we call as the basis of the linear vector space.
So this is
Set
a
of
set
all
of
Of
maximum
linearly independent
independent
vectors.
set.
Okay.
Sir,
This is the set of
linearly
vectors by which we can make the rest of the vectors, but with
Oh,
this
good. Okay.
basis.
So
sir,
let's just
linear.
write down the definition and then we will dissect the definition just like we have been dissecting everything. So a set, let's say, of n vectors in a n-dimensional linear vector space, or I should write in an n-dimensional linear vector space. So let me write this. Okay, I have a habit of writing something, so let me just use that. So U1, U2, let's say UN. So a set of n vectors in an n-dimensional linear vector space constitute a basis if B is linearly independent. Sensible? Or am I missing something? Oh, so let me just give another definition and figure out whether I'm missing something there. A set of n vectors. Now, please listen, read carefully. Set of n vectors in a linear vector space. So I'm not even writing n dimensional. So let's say V1. So V1, V2, Vn. So set of n vectors in a linear vector space constitute a basis if A B1 is linearly independent, and B1 spans LVS, that is any generic vector of LVS written in terms of B1. So now definition 1. So any question with that? Definition 2. Are these two definition same? Are we talking about something different? So anybody, is one definition correct? Is another definition correct? Or both the definitions are correct?
Second one seems correct. It's the complete.
No, sir, both are correct.
Second one seems correct. Both are correct. Anybody else?
Sir,
Both are
second
correct.
one.
Yeah. So
The
please
second one is
understand, please understand the way I wrote the definition. Both of these definitions are actually equivalent, and this is what we want to dissect. But let's just first try to understand definition number 2, and then we will see how to go ahead with that. So definition number 2 says a set of n vectors in a linear vector space constitute a basis if this set of n vectors is linearly independent set, and B, that this set spans the whole linear vector space. When I'm saying using the word spans, what does that mean? It means that any generic vector of linear vector space that can be written in terms of B1. So let me just try to continue writing on this portion. So if I take any general vector W,
Sir, what does span means?
this is what I am saying. Please listen to me. Then that W can be written in terms of the vectors of the set 1. Any general vector W can be written in terms of the vectors of set B1. So remember, our linear vector space consists of infinite many vectors. Yeah. If I take any one of those infinite many vectors, I can still write it in terms of this vectors which are given in this set. Remember our set. So yeah. Now, why would I say that? Do you understand the word span? Any general vector which can be written in terms of the linear combination of the vectors of the set. This is what we call spans. So the word span is, I mean, in some sense, you can think about this. So this is a vector space. I have a collection. I have a collection which I call a B1. If I keep on multiplying and adding with these alphas and then vectors, then I can generate this whole of the vector space. So starting from this set, I can generate whole of the vectors in the vector space. And that is what it means, that this set spans the whole linear vector space. You need to know only these V1, V2 and up to Vn, and then you keep on multiplying with the alphas and then keep on adding vectors using the, of course, rules. Then you are able to generate whole of the vector space. That is what it means, spans. That is, it generates the vector space. Just knowing the few vectors. Yeah. So question here, so that I can continue and so now how is it equivalent? How am I saying that my previous definition, which is a smaller definition, a set of n vectors in an n-dimensional linear vector space constitute a basis? So what's the catch in definition 1 that it is so small? Or I have written such.
The definition
Sir,
does
since
not.
the linear vector space of the first definition is n-dimensional, and the basis also consists of n vectors, it automatically spans the whole vector space.
Yes, sir.
Right. So this, thank you. Absolutely right, bingo. So this is what the catch was, that I already told you that it is an n-dimensional linear vector space. If I am saying that it is an n-dimensional linear vector space, what's the maximum number of linearly independent vectors it can hold?
and
N.
n, any additional vector if I add in that, then that set will be linearly dependent or linearly independent?
Dependent.
Linearly
That,
dependent.
Linearly
that
dependent.
becomes linearly dependent, which means that this set, which is already a set of n linearly independent vectors, irrespective of what these vectors are actually, this set will be able to span the whole n-dimensional linear vector space. And I can understand that this concept may be confusing for some. So let me do an example or give you an example which is more close to what you have been doing in your three-dimensional ones. So let's just do that example. So I have one set which I call E1, E2. I have another set which I call E1, E2, E3, and I have third set which is E1, E2, E3 with the additional one E1 plus E2 plus E3. And what is this E1, E2, E3? We are talking about R cube R space. What is R cube R space now? Can somebody tell me? It's a
Three-dimensional
Three-dimensional linear vector
right,
space.
three tuple of numbers or three-dimensional space, and this is the famous ones which you always use generally for the basis, but at this point of time we are trying to dissect our basis. So what we are doing, we have three vectors living in this R cube R space. One is 1 0 0, one is 0 1 0, it is 0 0 1. So these are three ones, and we have three sets which we have made. So I have question. Now question comes in the form. Question comes in this form. Is the set of vectors E1 and E2, so that is 1 0 0 and 0 1 0, linearly independent?
Yes,
set?
sir.
Yes.
How do you
Yes, sir.
How do you know? How do you prove that?
So the one of the vector set cannot be represented in form of other.
Forms.
That is one way, and the simplest way would be, how would you check if I ask you to check it?
Alpha 1 into S1.
Alpha.
Great,
Alpha
great. Yeah, so
alpha
do not forget that definition. I may keep on asking you that definition, so thank you. Yeah, but what you said was absolutely right. That since I gave for the linearly dependent another definition, so it makes sense. So this set is a linearly independent set. Now, question: does this set generate all the vectors of RQR?
No, sir.
No, sir.
No, sir.
Why would you say
No,
that?
sir.
Because it doesn't
For this
contain
S1,
R3.
Right.
the third vector will always be 0.
So right. So if I want to generate 0 0 z where z is not equal to 0, and I want to generate using my E1 and E2, I have a problem because E1 also has this 0 as the first one, third component, and E2 also has 0 as the third component. So any non-zero component I cannot generate from this, right? So this guy cannot span. Now question, this is linearly independent set, but this cannot span the vector space. Is it a basis? Is this set a basis?
No, sir.
No, sir.
No, sir. Okay, good. So let me just directly come to S3, right? So leaving S2. S3, is this set linearly dependent or linearly independent?
Linearly dependent.
Linearly dependent.
And what would be the basis of saying that?
The fourth vector can be represented as the addition of the first three vectors.
Right, this fourth vector is clearly, can be written clearly as the linear combination of the first three, and we have already seen the dependence of the linear dependence of the vectors. So S3 of course is not a linearly dependent set, but can S3 span all the vectors of the vector space, this R cube R?
Yes, sir.
Yes.
There is no problem in spanning now because you have this additional vector. So any vector we can write down and plus put 0 to that, and this will still be a vector of that. So this guy S3, this set S3 will be able to span it. Now, will you call this a basis?
Yes, sir.
No, sir.
So,
Yes, sir.
No.
What was the definition of the basis? Definition 2 which I gave. The set has to be linearly
Linearly
independent,
independent.
and then the set must span both have to be. So now question again, the set is not linearly independent, but the set spans vector space. So is it a basis?
No, sir.
No, sir.
It cannot be the basis. Now come to your famous S2. Is the set linearly independent?
Yes,
Yes,
sir.
sir.
Yes.
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 Does the set span?
Y-
Does the
Yes,
set
sir.
generate all the
Yes,
vectors?
sir.
Yes, sir.
Yes, sir.
Will it constitute a basis?
Yes,
Yes.
sir.
Yes, sir.
Yes.
Yes.
Yes, sir.
Yes, sir.
So go back to my previous page and take this definition 2 as the general one, the most generic one, that you generally try to see 2 points related with that vector space. Whether that set of vectors, that set is a linearly independent set or not, and whether that set spans the linear vector space. If any one of the property fails, then of course we cannot call it a basis for that linear vector space. So questions here so that I can move to the next one. Some other concepts related with basis. Okay, sounds clear. So let's just do. We have finite dimensional versus infinite dimensional basis. So this we should remember. So we have already seen certain finite dimensional basis. You have already mentioned that n cross p or n tuple of numbers. If I take collection of p infinity t, which means set of all polynomials which can extend up to infinity, and I will ask you the dimension of this basis, what will be this?
Infinity.
Yeah, because a naught
Yes, sir.
plus a1t, so on, a n t n, but this guy is not stopping, it is going up to infinity, right? So this guy has infinite dimensional base, but they are still countable, right? I mean, you can still count 1, 2, 3, so on and so forth. But then we can have continuous versus discrete basis. Now, what will be the discrete basis? Whether it is finite or countably infinite. This is the same definition which you have. So, if in a linear vector space, I have only 3, let's say, vectors, which describes or which spans whole of this or which is a basis for the vector space, then it is a finite basis. Of course, it's a discrete one. In the case of P infinity T, this is of course countably infinite. I can count A0, A1, A up to those A infinity count. What would be the continuous base?
Sir, uncountable infinite.
Uncountable infinite.
Infinite.
Can you give me any example?
Sir, set of real number over real field.
Set of real number over real field. Wouldn't this be described by, I mean, if this set, if you want to describe, this set will be described by this X, or I should most likely, such that this X belongs to real number. Wouldn't this set belong to this?
Sir, complex numbers.
Over?
Sir, over.
I mean, even if you put Z, then Z is defined by X plus IV. All you need two numbers, two real numbers, right? X, Y. So this is something as a homework, figure out. Out of
N over R.
R, N over R is N.
N approach
Fine.
to
So no, I am
N
not
approach to
asking for an
infinity.
answer right now. Please go back. Out of the examples which we did yesterday, which example will qualify under this continuous one? This is the question which I'm going to ask tomorrow. But please understand that when we talk about these bases, then we talk about finite dimensional versus infinite dimensional. Now, infinite dimensional is itself can be discrete or continuous. Discrete when I can count the number of elements which will be required to make that basis, and continuous when I cannot count. And I am asking you this question as a homework. So there are several books, for example, in the market which you can look at. Some of the books says finite dimensional vector spaces. That means those books deal with the finite dimensions only. Some of the book says infinite dimensional. Infinite dimensional don't immediately mean continuous. Infinite dimensional can be discrete depending on whether we can count the number of coefficients which are there. Okay, it can be continuous, for which I will ask for this example tomorrow. Okay, but questions related with finite dimensional or infinite dimensional or continuous versus discrete. This is only on the collection of vectors. Yes, please go ahead.
So can you please explain the continuous and the discrete basis? I got confused.
Unfortunately, I haven't given you an example because I'm asking you to figure out. Discrete countably infinite is the example I have already given, right?
Yes, sir.
Right, that is already there. Finite, you already have the example three-dimensional.
Yeah. Yes, sir.
So only thing which is left is continuous, right?
Yes, sir.
So once you give me your answer, then I will discuss about that. Does it make sense?
Okay, sir.
Yeah.
There is plane wave distribution.
Yes.
There is plane wave distribution.
Please go ahead. I mean, I am not asking for the answer right now, even though you are thinking in the right direction. But yes. Okay, let me just, yeah, somebody else is asking a question.
Yes, sir. Just tell me that when we talk about the dimension of a vector space, linear vector space, sir, if we say that, what is the dimension of that? You told the examples 2 or 3 that the dimension of vector space that containing polynomials is n plus 1. Sir, when we talk about dimension, then we just see the contains. I mean, if we say that dimension of vector space that containing matrices of 2 by 2, then we see its elements, matrix elements, that is 2 into 2 equals to 4, means it has 4.
So for set of polynomials, you are still having a little bit difficulty in understanding how the coefficients are describing the dimension. Yeah, that is the point.
There we just, I'm saying that
okay,
we just
I will describe the basis for polynomial, and then you will see. Just give me some time. And today's class itself, we are just going to finish it off. I'm sure that you will get your answer.
Sir.
Okay, now first question. If dimension of a given linear vector space is unique, so when I am saying that it is an n-dimensional space, is that dimension unique for that linear vector space, or you can have so set 1 with, let's say, 3 vectors, and another set 2, oh no, v1, v2, v3, v4, and all are non-zero, so it's non-trivial. I mean, it's not about the trivial ones, but the non-trivial ones. And 0, remember, doesn't make the linear dependence, so 0 cannot be part of the basis. So can the 2 sets be the basis for one given linear vector space?
No, sir.
No.
No, sir.
So dimension of the linear vector space is something which will always remain unique. Since we are talking about the maximum number of linearly independent vectors of that one, remember, so if you add more than 3 vectors in any space, then that vector set is always going to be linearly dependent. That means that is the way we saw it. For example, 3-dimensional vector space, I added the 4th one, that cannot remain linearly independent. So the dimension is always unique. Now question comes, is the basis unique? So actual set of vectors. So if I say V1, I mean, we already discussed one set E1, E2, E3 for a 3-dimensional vector space. This is what we discussed already. Remember E1, E2, Et. I just wrote it in the on the back side. So now, are these vectors unique?
No, sir.
No, sir.
No. And what can be another basis? for this three-dimensional one? Can you give me any other example? So let me write u1, u2, u3.
002, 200 or
So
others like that.
110.
110. Okay, for one. Another?
0,
0 1
011
101.
and 101
011 and
101.
101.
yeah, this is one which we did yesterday, and that is why I asked one. So this can be another one, or you can of course continue to make another one, 111, 110, or 100. You can continue to make those ones. In fact, there can be infinite number of vectors which will form basis for a given vector space. That's the interesting aspect. So basis vectors themselves are not unique, but the number of vectors lying in the basis, that is unique. So the important thing which is coming out of it is the basis itself is not unique, but so any set of three linearly independents will be there. But the number of vectors which are lying in that set, that will remain unique. So let me end this with a question. So now I give you n-dimensional linear vector space, and since it is an n-dimensional, my superscript, this is this one. So this is my linear vector space. Let me give you a set u1, u2, uk. So there is a set containing this. Fine. Such that k is greater than n. The question I am again asking, I have asked many times, can S1 be basis? If not, why?
Cannot
K
be a
is
basis.
S1 cannot be
Because
basis because
it cannot be
Because there must be
linearly
some vector in
independent.
It
S1
cannot
S1
have
is
that is
linear
not
and
linearly
n
independent.
dimensions.
So the dimension is not n now.
it is no, yeah, I mean, no, dimension is given. I mean, this is already given in the problem. So I cannot change that. So what you are saying that the maximum number of linearly independent vectors which this vector space V and F can hold is n, and this number cannot change. So we also call, somebody else was saying it, maximally independent set. So we call sometimes the basis as the maximally independent set. Okay, S2, another one. So we have V1, V2, Vm is the same. I mean the given n-dimensional linear vector space such that m is less than n. Will this form a basis? This is
No,
a
sir.
No,
linearly
No, sir.
No,
independent
It
set.
won't span.
no, sir.
it won't form a basis. It won't span the
It
whole
won't
vector
span over it.
space.
So that means this is the another definition of what we call as the basis. This we call as the minimally spanning set. So these two are other common definitions for writing a basis. Instead of writing two of those, I mean together, a set of n vectors in a linear vector space constitute a basis if B1 is linearly independent and B1 spans linear vector. B1 spans the whole space. Sometimes people call it, for example, that basis is nothing but a maximally independent set, or basis is nothing but a minimally spanning linearly independent set. So this is something what we call alternative definitions, but they all talk about the same thing. As long as we understand that set of vectors are linearly independent, set of vectors spans the whole space, we always put it as the basis. Okay. The last thing which I want to do in today's class is something, or before taking one question at least,
So
which I
can
will
you
give as
please
a homework.
explain this example again?
Which one?
This
S2?
one just.
S1?
Yes.
I mean, this is the example which actually, if you look into it, I have already done this. So what is the, and this is n-dimensional space, right?
Yes,
Right?
sir.
S3 is having how many vectors? 4, which is greater than 3. So you can take this as this one. Any set of 4
Okay, sir,
vectors
got it. Got it,
cannot
sir.
constitute, yes, and this S1 constitute my M, which is less than N, right? That set of 2 linearly independent vector, if it is less than 3, which is there as the dimension of this, then that cannot span the whole space. Yeah. So this
Yes,
is
sir.
the simple example basically explaining the same thing, but I just wanted to generalize it and ensure that you understand it. We are doing it at the post-graduation level, so we should be understanding it from all perspectives. That's the only idea. Okay, let's just go and do something. Once the basis is defined, now this is an interesting thing. Once basis is defined, so let's say we choose a set. So V1 of, let's say, V and F. So we are talking about n-dimensional linear vector space over any field, and I have chosen basis U1, U2, so on and so forth. Any vector can be written as the, this is the definition, this because this has to span. What are these alphas? Alpha 1, alpha 2, alpha n?
Scalars.
So they are scalars belonging to this field, whether real number or complex numbers, right? Now question, are these coefficients for a given vector unique or not? Are alpha I unique? Or I can expand the same vector W in terms of the same basis vector U1, U2, Un with some other coefficients also. So let's say beta 1, U1.
The coefficients are unique.
Coefficients are unique, and how will we prove that? So let's propose, just like the way we.
Because we can get like for example, if we take the example which you took earlier of E1, E2, E3, and we try to find any point in space using those, there will be only one value of alpha 1, alpha 2, alpha 3 which can point to
Absolutely
that
right. I
particular point.
agree with that. I agree with that, but I have to prove it using my first principles, right?
It will be around the concept of n equations and n variables, so there will only be one solution.
So you can equate both the equations and you'll get alpha 1 minus beta 1
Right. So what I am
U1
going to do
plus
is to
alpha 2
just
minus
do a
beta.
simple one, which you just mentioned, and let's just do it. So let's say that we propose that there exist beta i's such that I can also write this one, and I just take the difference of the two. So W minus W. What is the left hand side in that case?
Zero.
Null vector. So this is this. Remember, this will be W minus W, which according to my properties can be written as this, and this by definition is a zero vector. Okay, this side note. Now, what is the right hand side? This is alpha 1
Alpha
minus
minus
beta 1 U1 plus alpha 2 minus beta 2 U2 plus so on and so forth, alpha n minus beta n Un. Right? Now, what is this U1, U2, U3, Un? Look at this equation. What does this equation tell you? This is the famous equation for
Alpha 1
beta
equals
1.
beta 1, alpha 2 equals beta 2, and so on.
Why would it be?
Because they all have to be
U1
zero
is
if it
and
has to
alpha
Because
be
U1
linearly
is
independent.
dependent side. The basis.
Because
Linearly.
set
Linearly
B1 is a linearly independent set.
Independent. Yes, sir.
Hence, the coefficients of these U1, U2, Un have to be identically equal to 0. There is no other way. This is for the linear independent set definition. This means that alpha 1 is equal to alpha 2, or I can write alpha I is equal to beta I for all I is going from 1 to n. So this basically confirms that any general vector will be written as a unique combination, not any combination, unique combination of the basis vectors. Once the basis is defined, the coefficients alpha 1, alpha 2, alpha n are unique, which means what? Which means that now I can identify my vector W, for example, by something which I call that in this basis This is given by a collection of alpha 1, alpha 2 and tuple of scalars. In fact, I can now define my rules of addition in terms of just adding those n tuple of scalars. I can define my rule of, so if you think about, let's say there exists another one, z vector, then you can write down that once the basis is given. So let's say z be given by some betas which are not same. So this will be given by this. So instead of talking about the abstract vectors, I am just talking about now n scalars and tuples. I can multiply it by scalar. I will see do all the things which I can do with the vector. Instead of doing it with that, we can do it with the scalars. The only catch is that we are talking about a fixed basis. If the basis, which can be any linearly independent and linearly independent vectors, if the basis changes, then basically whole game changes. Then those alphas will not remain same, and hence everything with respect to scalars change. So basis, this is a short collection of vectors which will allow me to write all the other vectors in terms of that short collection. This also helps me in terms of working with the vectors, because now I can use anything in terms of just plain numbers. And this is the reason why I'm pretty sure that all of you remember that instead of writing like this, we also represent it like this, as long as we are talking about a particular. Yeah. But if you change the directions, then of course these numbers will change. So this we'll have to remember, and I will end my class with a question which I want to give you. And this will answer this polynomial thing also. Fine. Now, the question which is coming to you is this one. So I am giving you polynomial space question because I just now want to do problems with the polynomial, and I can explain that also. So let us consider P to T. What will be this P to T? P to T.
Polynomial of second degree.
Dimension
So what will be the dimension?
3, 3.
2,
3.
3.
3.
3.
Right.
3 dimensions.
So let me give you now a set, and there while giving you the question, I will just explain the concept also. So E1 is equal to 1, E2 is equal to T, and E3 is equal to T square. So remember, these are vectors of this polynomial space, and I have given you three vectors, 1, T and T square. Another set S2, U1, U2, U3 in the same space. So U1 is given as T square plus 1, U2 is given as, okay, let me write explicitly, T minus 1, and U3 is written as 2T plus 2. These vectors all live in the same P to T space, that is obvious. Now let me ask questions like this. 1. Is S1 linearly independent? Is S2 linearly independent? So these part A, part B of the question. 2. Can S1 be basis for P to T? What about S2? Okay. And third, a general polynomial is given as, okay, so this is how I want to write, 6t square plus 7t plus 9. I want to know the component vector of W with respect to S1, and I also want to know the component vector with respect to S2. And my final question, this is a bigger question, but it's not that tough. I want E1 with respect to S1, each of the vector of those vector spaces with respect to S1, E3 with respect to S1, and the same with respect to S2. And I can continue to build my problem U1 with respect to S1, S2, U2. I hope you got the gist of the question. Just to appreciate what we have been saying. So let me just finish it off the question. Okay. So first set, is the set linearly independent? Now I have given you the dimension already. What is the dimension? 3. So how many vectors do you require? In this case, you are already clear. 3. So all you need to check is the linear independence of the vectors to figure out whether this set can qualify as a basis or not. Because 3 vectors can always generate that basis. Right. Now question 1, which is a trivial one. E1, E2, E3. Does that is SI
Linearly
Yes, it is
independent.
independent.
and that means can S1 be the basis?
Yes,
Independent.
it can.
Sure.
Yes,
So
sir.
this is something which you have been traditionally doing. And at this point, I want to explain the question of this P and T, that when we are talking about P and T as the linear vector space, then we talk about 1 T T square as the basis and not the coefficient as the basis. The basis of the polynomial group or vector space has to be polynomial. This one is a polynomial, T is a polynomial, T square is a polynomial, and you will continue to build it. So the most generic way of understanding that P and T is a polynomial of n plus 1 dimension is, so how? So when you are writing 1 plus, so A naught plus A1t plus A2t square plus A n t n, then what you are saying is that each of this polynomial, if you think about that, this set which consists of 1 t t square t cube t n constitute a basis, because there is no way I can write 1 in terms of t. I cannot write t in terms of t square. So this has to form a basis, and hence this is collection of n plus 1 vectors which constitute basis for this polynomial vector space. Remember, the polynomial vector space has to have less than equal to n and not exactly fixed n. So does this answer the question which was raised in between, that how n plus 1 vectors constitute basis for a polynomial space? Somebody asked it in between and I said I will answer it towards the end. Does it answer this? Okay, that person is no longer there. So can you please say it again? So while giving this question, I mean, okay, I mean, I do this question, come back to me tomorrow, give the answers to this question, and we will discuss. If you will say 1 t t square is the basis for p to t, then you will understand 1 t t square up to tn will be the basis for p and t, right? I mean, that will be a simple extension. So let's just do that. But any question, any problem with any part which is difficult for, I mean, which you are unable to understand in terms of the question?
What exactly do we have to do in the fourth part? Like, can you tell
In
in
the third
words?
part, what are you supposed to do in the third part? There is a general polynomial 60 square plus 60, 70 plus 9, right? And I'm asking you to give me in terms of the component. Remember, how do I define my component? That you are going to write down the collection of n tuples. In this case, the dimension is 3. So how many numbers?
3.
3, right? 3 numbers. So there will be 3 numbers for this one, and that dimension cannot change. So there will be 3 numbers for this one also, right? For S2. Similarly, E1 is also a vector of this space. It's a polynomial, right? 1 is a polynomial. Just like the way you are going to give me numbers, 3 numbers for this one, WS with respect to S1 or S2, you can give me the same numbers for my E1, for my E2, so on and so forth. Yeah, it is exactly like 3. It is just that it's the way it is given, it looks like that the basis may or may not be polynomial. Sometimes people have this problem of understanding that, and I am just trying to take care of it. So fine, I mean, this is where I end. my today's class. If you have questions, yeah, if you have questions, please ask it.
You can go to the previous slide, sir. Just previous.
Yes.
Sir, here if you define W minus W, so it is coming 0, null vector. So
Yes.
if we are defining the scalar multiplication as alpha W is equal to alpha into A comma 0. So if
alpha W is equal to alpha minus 0.
no, sir, alpha into A, W containing A and B. If W is containing A and B,
W is containing A and B. What is that A and B? How should I write it? I mean just
tuples.
So this number.
Yes, sir. A and
Right.
B. So if we just taking the scalar multiplication, then it goes to the A into alpha comma 0.
Oh, right. Oh, okay. Sorry. I mean, I should not write it like this because I'm explicit at this point of time. So what I would write in that case is this. Now I understand your question. I would write like this. Alpha W, because that has to be in a given basis. If I change the basis, those numbers will change. And hence, I would like to write always in terms of the basis. And now you can say yes. If alpha A and alpha B, if your W is represented by, sorry, A comma B. Yes, this is exactly right. You have a, oh, so you are basically asking question related with that when we are doing the upper part, that I did my vector addition up to this point, right? So if I do the multiplication with a scalar alpha omega or W, then how that will be represented? Yeah. So
And also, sir, there is a problem with if we are taking that definition, if we considering that definition,
that is
so the second term is coming 0, and we are when taking the minus sign, and -1 is our alpha is equal to -1.
Previous page. This is.
Yes, sir. On the previous page, if
Yeah.
taking that alpha is -1. So my second term here, if my definition of the vector spaces is different than whatever you write, sir, it is alpha A comma 0.
Alpha A. Let me just continue to write. So others may leave. I will discuss with you. Yeah. Okay. So then I take next page and now I write in green. Yes. So please ask me. Others can leave and join the other class. Yes. I let me just discuss. Yes. What do you want to say? Alpha
W.
Please.
Yes, sir.
Vector
is equal to
right.
A alpha comma 0, and W is containing A and
E alpha and 0.
A alpha, whatever. If W is my A comma V, then we are
A
defining
comma B. I mean,
yes,
you are saying.
sorry,
Yeah. So yeah, since we are only speaking, so that is making my life little bit tough. But let me just continue to write. Okay. So W is given as the collection of two numbers, A, B, and alpha A, alpha B. Yes. Yes. Go ahead.
yes, sir. So if we are taking the
So beta W, if I am taking, and then you say I write beta A,
comma 0.
B.
Not if I defining other things. Sir. Second term is 0, sir. If we are taking the y coordinate, we say.
This B has to be 0.
Yes, second coordinate is 0. We are taking that definition is like that, sir. If we are taking like.
So if I define it as A and 0. You are saying like this?
Sir, if
because see, my problem with this is this. Let me just tell you the way I am trying to say it. So let's say if there are only two vectors, right? P, U2. The only way you will have, I mean, non-linear independence U1, U2. The only way you have linear independence U1, U2 is that both A and B have to be 0. Right? This is up to this we are fine.
Yes, sir, it is fine.
Okay. Now, when you are writing, expanding it, let's say U1, U2 constitute my basis. Fine. This constitute my basis. Fine.
Yes, sir. Yes, sir.
Now, if I am writing it, let's say alpha u1 plus beta u2, there is no way you are going to put this point as the 0, because this will look like as if this guy is 0 vector. So then the linear independence of u1 u2 itself is in tough state. This is what you are saying, or you are saying, okay, these are just the coefficients a and b which are 0.
So actually W is containing A and B both, but we are defining a scalar multiplication by it ourselves. In the vector space, we are defining a scalar multiplication, and since we have given scalar addition and scalar, sorry.
No, but let me first ask you, then in that case, let me first ask you,
Yes,
what's
sir.
the problem which you have, and then I will understand, and then I will try to explain.
So actually, sir,
You first
if we
speak out and then I will say that.
yes, sir. So actually, if we are taking the means alpha means scalar multiplication, if we are taking as a into alpha comma 0, like that definition. So yes, sir, it is a alpha comma 0, like this definition. So if
Yes.
we are taking alpha is equal to -1, so it coming minus a comma 0, and W is containing a comma b, and when we are subtracting them, because we are taking the vector addition after that, the closure
No, but who told you
property.
that this is constituting a linear vector space? No, I haven't got it. Who told you that this is constituting linear vector space?
It is a question in, sir. We have to first
Yeah,
prove
that's
that.
what I would suggest. That's what I would suggest. I can understand that. I mean, what you are saying is this. Let me just explain your question, and then you post it to me separately rather than we're doing here.
Okay, sir.
Your question is this. A linear vector space is defined with a given vector addition and a given scalar multiplication. And that given vector addition and given vector scalar multiplication is what you are giving to me.
Definitely,
Yeah.
yes. This is
Now, my first point would be, how do I know that what you are saying is constituting a linear vector space? So you need to do more than that. You need to first show me that this actually constitutes a linear vector space.
linear vector space. Yes.
Once you show that this constitutes a linear vector space, I will tell you that if I am going to have the basis in this linear vector space, it is going to follow all the arguments which I am giving. But the first thing has to be there. It has to be a linear vector space. I cannot talk beyond linear vector space for the basis. Basis will surely generate your linear vector space, but basis cannot generate anything which is not in the linear, which is not a linear vector space. The algebraic structure is such that the three-dimensional vector space, if you keep in your mind, just the way you keep it in mind, all the vectors can be uniquely written by certain numbers, and I can add those numbers and I will get exactly this. So if I add those numbers, I mean, remember, so if this resultant is a vector, I can get this just by adding the numbers which are there in the parenthesis. So if I add these, I will actually get this vector. This is how we define the vector spaces, or three-dimensional vector, right? This is the Euclidean vector. That is why you are able to do it in terms of a given basis. Yes, in terms of a given basis, surely.
Yes.
But if you go beyond that, I need to first qualify it as a linear vector space. If I can do that, then I will show you this will always be true. But I do not know whether what you are talking about is actually making a linear vector space or not. I understand what you are saying is this. So there exists something like this, and I am defining. So this is my definition. Is A alpha 0? And what about the vector addition?
It is simply the A1 B1 and A2 B2 if W and W2.
So
then
let's say
E1 plus
C
E2.
and D. So A plus C and B plus D.
Yes, sir. Yes, sir.
So if your Z is C and D, and these are all real numbers. I mean, these A, B, C, D. I mean, it
Yes,
is
sir,
on
it is
the
defined
real number
over.
space.
Yes, sir.
So you have something like R square R kind of a space, but of course your definition is some. So this definition is a usual plus, but this definition is an unusual one. So did you check whether this qualify to be a linear vector space?
So that is the problem, sir, because if we are checking only for the since if we are taking any vector inverse of that, if by the definition it should be minus a comma 0 if we are taking the inverse of any vector.
Right, because what you are saying that the null vector of this space is 0, 0. Right, this is the null vector of this space. You are defining your addition very regularly. But is this becoming a null vector when I am multiplied by any number? Yeah, I mean, if you are multiplying by 0, it is still coming out to be 0. So this will at least be consistent with this portion.
Yes.
So yeah, but you have to see all those 10 properties. Those are matching. This particularly the distributive properties, since it's about the scalar multiplication, which is different. So I know that all the properties related with your regular associative ones and the existence of this, that will be there. But is it matching all the distributive properties?
No, sir. No, sir.
So then you won't be able to qualify it as a linear vector space, na?
Yes, sir.
So which property you found it to be failing?
Actually, the inverse one is failing because if we are taking
minus W.
Yes, sir.
Which
Because
is equal to
minus
minus
W,
1
minus
W,
1 to
which
W.
is equal to, if I go from this definition, A equal 0, which by my addition is minus A minus B.
Yes, sir. Yes, sir.
So this cannot be the inverse, because minus A 0, if I add to AB, then it is not giving me 0, because if I add W plus minus W, then this will be, so AB plus minus A0. This is which is coming from here, which is 0 B, which is not the 0 vector. Hence, this space does not qualify to be a linear vector space.
Yes, sir. Yes, sir.
So this is the question which you are doing, and so we
Yes.
discussed the answer. Okay.
Yes.
Fine.
Yes,
I mean, yeah, but once it is not a linear vector space, I cannot talk about a basis in that space. Yeah, I mean, you understand that.
Okay, sir.
Okay, yeah. So since I could not figure out, I thought that your question is related with basis, and hence I could not figure out what you are exactly asking about. Okay. Anyway, it does make sense that this question is about whether a particular space with the certain rule of addition, vector addition, and scalar multiplication qualify to be a linear vector space. You will answer it. It is not, and it is failing this or maybe some other properties as well.
Yes.
Good. Okay. Good.
Hello, sir.
Yes. Oh, you haven't gone to other class?
I also
Let me,
no, sir.
yeah.
I have also heard
So
that.
let me first stop recording, because then the teacher will tell me that you continue to
Okay.
take class after the class also. So, yeah.